Hi everyone, and welcome to this 6th episode on the Mandlbaur insanity. For those who haven't seen the previous episodes, let me give a brief summary in a single sentence. John Mandlbaur is a guy who thinks he's more intelligent than Newton. Okay, let's look at your rag, Mr. John Mandlbaur. You claim that the work energy principle is false, and to arrive to your wrong conclusion, you consider a rocket to which a constant force is applied, and you calculate the work done over a distance of 5 meters and compare it to the work done over a distance of 100 meters. And you seem to be surprised that the work done over 100 meters is 20 times the work done over 5 meters. Well, that's trivial. This result comes from the definition of work, which for a constant force is proportional to the distance. Then you say that if the 5-meter distance at the beginning and the 100-meter distance sometime later are both covered in 1 second, then the energy spent by the rocket in both instances must be the same. That's right. So what? You are simply proving to us that you don't know what the work energy principle is. There is nothing that says that the work done by the force must be equal to the energy spent by the rocket. That's your first mistake in this problem. Second, what the work energy principle says is that the work done by the net force on a given mass is equal to the change of the mass's kinetic energy. And trying to apply this version of the principle to your rocket that has a varying mass is your second mistake. You need to use a generalized version of the principle for varying mass. This is what I'm going to do in the following in order to prove you wrong once again. But before that, let me prove that by claiming that the work energy principle is false, you are just contradicting yourself. Indeed, in another of your rags, which you call the perfectly well-written and undefeated proof of your non-existent discovery, you are making use of the well-known expression of the kinetic energy. So, this means that you agree that this is the correct expression of the kinetic energy. But do you have any clue where this expression comes from? It comes from the definition of the work done by a force in order to accelerate a mass initially at rest to some speed. By definition, the work done by the net force to accelerate a mass m from rest to some speed v is given by the integral of the net force over any path. From Newton's second law, we can substitute the mass times the acceleration for the net force. And if the mass is constant, then it can be taken out of the integral. The acceleration can be replaced by its definition as the time derivative of the velocity, while the infinitesimal displacement can be replaced by the instantaneous velocity times the infinitesimal time. And it doesn't take a genius to conclude that the result of this integral is 1/2 of mv squared. Now, the only thing that remains in order to obtain the work energy principle is to apply this definition of the kinetic energy 2 times for some initial and final speeds and take the difference. On the left-hand side, we get by definition the work done to accelerate the mass from the initial speed to the final speed. And on the right-hand side, we obtain by definition the change in kinetic energy. So you're wrong, Mr. John Mandlbaur. You are contradicting yourself. No, don't cry yet. I'm not done. I'm going to destroy you even more. Before showing you what the work energy principle is in the case of your rocket, let us check experimentally that the work energy principle works as it should for a constant mass. I have here a cord with a fan that applies a force on it, and that I used in a previous video in which I destroyed your claim that Newton's laws are wrong. And I have here a force sensor that I also used in a previous video to destroy your claims. I'm going to use it to measure the force on the cord and to check that it is constant. The computer displays here the instantaneous force, which currently is nearly zero, with an uncertainty of only 5 millinewtons. I'm now holding the force sensor and get the computer ready to collect data. And we can see that the force quickly becomes constant, so let us look closely at the data. I'm going to select the region where the force is stabilized so that I can get a good estimate of this force by looking at its mean value. I have 0.1649 newtons, so I'm going to round it to 3 sig figs as 0.165 newtons. Now that I know the force that the fan applies onto the cord, I'm going to record the position and velocity as functions of time with a motion detector and see whether they are in agreement with the work energy principle or not. The computer is set up to automatically record the data once the cord is within a distance of 1.5 meters from the detector. The computer collected the data, so let us give a closer look. I'm going to test the work energy principle to a random choice for the initial and final times. And if you don't like my choice, feel free to take any other pair of initial and final values that you can see from these data. The principle should work for any choice. So here I choose 0.30 seconds my initial time and 0.95 seconds the final time. The initial position and speeds are 1.349 meters with a speed of 0.498 meters per second. And for the final values we get 0.961 meters and a final velocity of 0.695 meters per second. This way we can calculate the distance, and since the force is constant, the work done during that time interval is simply the force times the distance. So we get a value of 0.0640 joules. Now if we calculate the change in kinetic energy, final kinetic energy minus initial kinetic energy, we get 0.0642 joules. So the percent difference is only 0.3. That's not bad for such a simple experiment. You're wrong, Mr. John Mandlbaur. The work energy principle is correct. But now let us look at your rocket. Once again, the work energy principle that expresses the work done by the net force as the change in kinetic energy assumes that the mass is constant. You cannot apply it to your rocket. In order to express the work done on a rocket as a function of initial and final speeds, it is necessary to go back to the definition of work as the integral of the net force over some path. We can substitute the mass times the acceleration for the net force, and we can substitute the instantaneous velocity times the differential time for the differential displacement. But since the mass depends on time, we cannot take it out of the integral. In order to calculate the integral, we need to know how the mass, acceleration, and velocity depend on time. In order to determine these quantities, let us look at how a rocket is actually propelled. We are going to assume here that it expels gases at constant velocity, Vt, where the subscript stands for thrust. Let us consider an observer at rest on the starting platform and who describes the situation at 2 consecutive instants. So, at a certain time t, he sees the rocket with a total mass m moving at velocity v. 1 instant dt later, the speed of the rocket increased by an infinitesimal value dv, and its mass decreased by an infinitesimal value dm. At the same time, a mass dm of gases has been expelled at velocity vt with respect to the rocket. So the velocity of these gases with respect to the observer is the velocity of the rocket minus vt. The momentum at time t is the product of the mass and the velocity that the rocket had at that time, thus mv. At time t plus dt, the momentum is the new mass of the rocket times the new speed, and we need to add the momentum of the gases expelled, which is equal to their mass dm times their velocity v plus dv minus vt. Now, since the rocket and the gases that it expelled are in vacuum, they constitute an isolated system, so the net force on it is zero. This means that the momentum of the system is conserved, from which we conclude that the infinitesimal change in velocity is dv equals vt times dm over m. But we know that the gases are expelled at constant velocity, which implies that the mass of the rocket decreases linearly. Thus, the mass as a function of time is equal to the initial mass m0 minus the burning rate alpha times t. With this last piece of information, we can integrate the velocity and find that it is equal to the thrust velocity vt times the natural logarithm of the ratio of the initial mass to the current mass. It is now easy to obtain the acceleration by taking the time derivative of the velocity, and the obtained expression reveals that this acceleration is not constant since it depends on the varying mass. However, if we plug it into Newton's second equation, the varying mass cancels out and the force is constant, as expected. And finally, we can obtain the position as a function of time by integrating the velocity. Now that we have all the kinematic equations, we can derive the modified expression of the work-energy principle for the case of an object whose mass decreases linearly, such as for a rocket. Since, as we have shown, the force on the rocket is constant, the work done from an initial position to a final position is simply equal to the force times the distance traveled. But we can evaluate this work in a second way by integrating the mass times the acceleration times the velocity over the time between the initial and final state, and we obtain an expression that depends only on the initial and final speeds. And we can clearly see here that this expression has nothing to do with the energy spent by the rocket, which obviously is proportional to time. So, as usual, you're wrong, Mr. John Mandlbaur. The existing theory never said that the work must be equal to the energy spent by the rocket. What the theory says is that the two expressions shown are equal, and it is very easy to check that this is true. For this, let us take some arbitrary values for the thrust speed, the initial mass, and the burning rate. And if you don't like these values, feel free to change them. It will work as well. If we look at the trip during the first second, we can calculate the initial and final positions and speeds to be the ones shown. The rocket traveled nearly a half meter and ends up with a speed of nearly 1 meter per second. And if you plug these values into the two expressions for the work done, you can check that you get exactly the same value. Now, 10 seconds later, if we look at the trip over 1 second, we find these initial and final positions and speeds. So, the distance traveled has increased to about 10.8 meters, and the speed is about 10 times what it was at the end of the first trip. And if you plug these values into the two expressions for the work done, we find again a perfect agreement. Let me summarize what just happened, Mr. John Mandlbaur. I showed that you don't know what the work-energy principle is, and yet you pretend it is false. I showed that By claiming that the work energy principle is false, you are contradicting the expression of the kinetic energy that you accepted as being correct. I made an experiment that clearly supports the validity of the work energy principle. In your rag, you proved to us that you ignore that the mass of a rocket varies. You proved to us that you don't know that the work energy principle, which expresses the work done by the net force onto a given mass in terms of a change in kinetic energy, applies only to a constant mass. You don't know that the energy spent by a rocket is not the same as its change in kinetic energy. In other words, you have absolutely no clue of what you are trying to talk about. Go ahead, now you can cry.